Good morning, everyone. Myself is P. Bharani Chandrakumar, and I am a faculty at GMRIT Institute of Technology. This particular lecture is a supplementary file 1 for the video recording. So this is a part of 1 week online unique hands-on SDP on control system design from a beginner to an expert, SDP 1.0. So yesterday we have discussed how to build a simple model and how to design a feedback controller for that one. So here again we will design, instead of only the proportional controller, the gain controller, today we will design a PID controller for a simple transfer function. To start with, this is the old plant. You can see g of s equal to 1 by s into s plus 5, so which is nothing but 1 by s square plus 5s. And the new plant what I have considered here is g of s equal to 1 by s square plus 5s plus 1. So another plus 1 has been added here. So the key difference is the addition of this one as compared to the old plant. So now we will design the controller for this one. We will not start from the scratch, rather we will build up upon the things what we have learned in the day one. So this is basically the Simulink block diagram for the PID control feedback system. So you can see that this is the plant where we can, yesterday in the last class we have not seen this plus 1, this plus 1 is there, and in the last class we have only seen the gain here. Now it is a PID controller, so remaining everything is the same. We have taken 3 different cases. The first one is only the proportional controller, the integral and derivative I assumed as a 0. In the next one I assumed KD as derivative control as 0, and in the third one all the 3 I kept. So we will see how to build this one. So this is the one what I was discussing. So this is the yesterday's one. You can see that plus 1 is not there and plus 1 is there. What we will do here is we will replace the same controller. We will keep the same controller and we will replace the plant, and we'll see what is happening, and then we'll design the PID controller for that one. To start with, let's go to the MATLAB, and I will, whatever the yesterday we have done, I will just open this one. This is the yesterday's plant, you might be remembering. So now what I'm going to do here is I will just double click this one, and since the last term is 1, so instead of this 0 I will make it as 1, and I will just apply OK. And since this now expression is bit larger, so it is not visible, so you can just drag this one. Now I'm going to run this one. If once I run this one, this you can see that in the last case when there was older transfer function, it was settling at 1, but now it is not settling. So this why it is not settling, this has been discussed in the class. So now this is one such case. Now what I'm going to do here is I will replace this with the PID controller, and for various gains we'll see what is happening. So to get the PID controller, just click this Simulink browser and just type PID. I will type it again, PID, enter. So as soon as enter, you will get this thing. For different versions you will have different types of things, but you just take this PID controller, add to the block, and now delete this one, and now you connect it. So this is my PID block. The parameters, PID parameters, by default it will be having 1, 1, 0 and 100. So now what I want here is, so I want the I want to design the PID controller step by step. So first I will do this KP equal to 10. This is very much similar to the one, only the constant gain. We will see what is happening. So what I'm going to do here is KP equal to 10, the KI and KD as 0. So what I will keep as 10, KI as 0 and 0, and this is the filter, this is the approximation of the derivative function what we discussed earlier. Just I'm keeping it as 1 by 100. Now if I will run this one, then you can see that the same thing with the gain of constant, and this PID will act as a proportional because we assumed as integral and derivative as 0. So this is the one. So the problem here is the steady state error is not 0. In the second case, what I will do here is, in the second case, remind you can just save it with closed loop plant. You can save with some PID controller underscore PID PID underscore D2. Okay, so now what I am interested here, we have seen one such aspect. Another aspect what we'll see is we will include the integral 5 and we will see what is happening. So the important thing to observe here is that the steady state error is not 0. That means it is because this value is not going to 1. So now I will introduce the integral gain of 5, that is the case number 2. You can see the case number 2 here. Case number 2 is 10 and 5, the KD is 0. So that's what I did here, 10 and 5, and it is 0. And now I will run and I will see what is happening. And if I run and if I see the output, you can see that the system is, it is good. The steady state error has gone 0. So there is no steady state error, whereas in that earlier one proportional case there was a steady state error. And now what I will do here is I will include the derivative gain as 200. I will include the derivative gain as well here of 200. And then if I run this one, then you can see that although the PI and PID will look very similar, but they are not. That's what we will see now. So this is how you will design the PID controller, and how to design these gains we will discuss in the next class. So now if I run the 3 cases, if I capture, if I plot and if I capture it, so it will look like this: 1, 2, 3. So the proportional controller, you can see that if you see the proportional controller and PI controller and PID controller, you can see when you use only proportional controller, the error is 10%. That means instead of 1 it is going to 0.9, whereas in both the cases it is steady state error is 0. You can see that the PID controller has slight improvement over PI controller in terms of rise time, in terms of peak overshoot, and in terms of settling time as well. There is an improvement. However, you can see that the proportional controller is very good. There is little bit you can, if you want to sacrifice rise time as compared to this one, this is fine. But the good thing here is the overshoot is very less, settling time is also very less. But the bad thing is it has a very large steady state error, which is not desirable for this particular application. So that's it from my side. Thank you very much. Good morning everyone. Myself is P. Bharani Chandra Kumar, and I am a faculty at GMRIT Institute of Technology.